Howdy. Today we are diving into ESCRA, a breakthrough system that makes cloud resource allocation as smart as a luxury hotel's real-time room service. Imagine that the hotel is a data center. Each guest is a container needing resources. CPU is their room size and memory is their amenities. The main challenge is we do not know who will throw a party, burst workload, or who will check out early, short-lived task. It is completely random based upon the customers or the containers that we have in our data center. Based upon this, we have two main problems that this paper discusses upon. One is the overprovision of rooms, that is having a luxury suite that no one can afford, expensive. This in turn leads to wasted money, that is cloud costs rocket, or under provisioning, where guests are being forced to stay upon in tiny rooms, that is guests crash, problem, or they wait forever to get a room for them to be allocated, that is throttling. ESCRA fixes this with smart real-time sensors. Like a five-star hotel manager, it can instantly detect needs. There is no wait for each of the containers, adjust resources live, there is no container restarts, and balances the whole hotel. That is global resource sharing. Now, let's see how ESCRA outshines the existing systems. Current tools like static allocation or autopilot are like slow, clumsy hotel staff in cases where static allocation is that we have fixed CPU or memory limits. That means they are like rigid rooms that never change and we cannot change their size too. Or vertical pod autoscaler, which needs to upgrade its containers for every 5 minutes, but it can happen only if those containers restart. Or in case of autopilot, the autopilot uses ML prediction but always misses the outburst in the sense that it misses the outputs of data, or in our case, surprise parties. And it also goes through every 5-minute intervals. So if any customer hosts a party within this 5-second interval, that is if there is any problem or throttling in case of our data centers within this 5 minutes interval, then the ML predictions or the static allocation misses it. ESCRA wins by reacting to live events. It does not depend on predictions or scheduling, and it also uses extremely smaller time intervals like 100 millisecond adjustments. This paper mainly discusses on 4 main key innovations that upon which this ESCRA model or architecture is being built. The ESCRA's magic lies in 4 innovations, that is fine-grained telemetry. It uses Linux kernel hooks to track CPU or memory every 100 milliseconds, exactly like a live fitness tracker for containers. Event-driven scaling. If a container starts throttling, then ESCRA adds CPU before we notice a lag. Distributed containers. Idle resources are shared globally, like repurposing empty suites for crowded parties, like we saw in our hotel case. In distributed containers, if we find any containers that is without any data, that it is ideal, then that container can be allocated to another container which is extremely busy and it's overflowing with data. And proactive reclamation. ESCRA cleans up unused memory automatically, which leads to no waste, which also reduces slack. So, based upon these 4 innovations, the ESCRA architecture has been built. If we say this project in one sentence, we can call ESCRA to be a real-time event-driven orchestrator that containers deserve. It's like upgrading from a sundial to a stopwatch, and it has been open sourced for anyone and everyone. Let us take a look into how this ESCRA is being implemented and its architecture.
Let's go over the architecture of ESCRA and how all the components interact with each other. ESCRA is designed to integrate seamlessly into existing cloud native environments, and that starts with being built top on Kubernetes. This means you don't need to redesign your stack to use it. ESCRA works with the orchestration platform most modern infrastructure already rely on. Now, when ESCRA deploys an application, it treats it as a group of containers, each representing different components. So one container could be like a backend service, another could be a database. But all these containers are governed under a single resource budget. And importantly, ESCRA is optimized for single tenant deployments. What does that mean? It means that it focuses on maximizing performance and efficiency within one application. Now, ESCRA's architecture is divided into two major parts, the control node and the worker nodes. The control node is where ESCRA's brains live. This is where all coordination and decision making happens. It contains three key components. One is the application deployer, then the controller, and the resource allocator. We'll shortly look at how each of these components work. On the other side, we have the worker nodes where the actual application containers run, like your backend services, databases, or worker components. Each container on a worker node is paired with a local agent and a kernel hook system. This is how the complete architecture looks like. Now, let's see each component one by one and how they interact with each other. The application deployed is ESCRA's starting point. It reads the application's YAML file, which contains a full set of container specifications along with global CPU and memory limits for the application. These global limits are then sent to the controller so that ESCRA has a centralized view of the maximum resources available for allocation. To bootstrap each container, ESCRA then assigns initial CPU and memory using a simple formula. As you can see here, the CPU limit is evenly divided across containers, and the memory limit is divided similarly, but it is scaled by a safety margin factor, sigma, to reserve headroom for containers that might face memory pressure later. Once these limits are set, the deploy triggers Kubernetes to schedule and launch all containers across available worker nodes. Once the containers are deployed by Kubernetes, ESCRA's container watcher steps. It continuously monitors the cluster using the Kubernetes API, and as soon as a new container comes online, it immediately notifies the local agent running on the same worker. This notification is critical because it allows the agent to begin setting up monitoring and resource control for that container right from the start, and that ensures that no container runs unmanaged. But what is this agent exactly? So, the agent is a lightweight user space process that runs on every worker node alongside the application container. Kubernetes by default lacks the ability to adjust CPU and memory kit dynamically at a fine grained level during runtime. That's where the agent comes in. It acts as a bridge between the controller and the Linux kernel. It's a component that actually applies changes like increasing memory limits or reducing CPU quota. So, how does this agent do exactly? To do this, the agent uses something called kernel hooks. These kernel hooks extend the functionality of the Linux kernel without modifying its source code. This allows ESCRA to observe and act on key container level events with minimal overhead. With the help of this kernel hook, ESCRA does three system calls. First, it sets up a TCP kernel socket to the controller. This registers the container and the socket stays open throughout its life. Second, it hooks into the completely fair scheduler, which is the Linux's CPU scheduling mechanism. This allows ESCRA to collect detailed CPU data for every scheduling period, namely usage, quota, throttling events, and unused time, and writes them into a FIFO buffer. This data is then sent to the controller. And third, it hooks into the container's memory C group. If the container is about to exceed its memory limit, this hook catches the OM event even before it results in termination and sends it over the TCP socket. Now the data is sent to the controller. The controller is the central coordinator in ESCRA's architecture. When a new container registers, the controller creates a logical container object, which is like a software representation that keeps track of its resource limit. It then collects and stores fine grained telemetry. The controller also proactively reclaims unused memory. Every few seconds, it checks whether containers are holding on to more memory than they actually use. If so, it reduces their limits. Finally, the controller forwards all telemetry and memory data to the resource allocator. When the controller detects that a container is running out of memory, it sends an alert to the resource allocator. In response, the allocator first checks the global memory pool to see if there is additional space available. If space is available, it increases the memory limits for the affected container to prevent further memory issues. After making this decision, the resource allocator then communicates with the controller and instructs it to update the container's resource limit. Now let's try to understand how the resource allocator makes a choice on updating the resources. For dynamic CPU allocation, the algorithm behind this component uses real-time CPU telemetry from containers, and then it ensures that the system stays within a maximum CPU limit, which is here denoted by omega L. By continuously monitoring and adjusting based on container performance, this approach optimizes resource usage. So here's how it works. For each container CI, during period T, the runtime statistics are collected. Namely, we collect the CPU quota allocated to the container in milliseconds, then the unused runtime in milliseconds, and finally the throttling status, which is basically set to 1 if the container is throttled, otherwise 0. So, if the throttling status is set to 1 in previous period, it means that the container is throttled and the algorithm will increase the CPU quota for the next period. The new quota is determined by the following formula, where omega L is the maximum CPU limit, epsilon is the scaling up factor, and lambda is the total number of containers. On the other hand, if a container's quota exceeds its actual usage, then we reduce its CPU quota for the next period. Specifically, if the container has unused quota beyond a certain threshold, the overprovisioning threshold, then the new quota is decreased using this formula given here. And here, kappa is the scaling down factor. So, similarly, for memory allocation. So, for memory allocation, the resource allocator has two main responsibilities. First is to be reactive by allocating more memory to containers that are under memory pressure. And second is to be proactive by periodically reclaiming unused memory from containers that have been allocated more than they actually need. So, when an out of memory event is triggered by containers, the CI, the resource allocator first checks the global memory pool to see if there's any unallocated memory available. If yes, it directly allocate to the container that needs it. If not, then the allocator will request the controller to reclaim memory from other containers. Now, when the memory is being reclaimed, if the controller is able to get it successfully, then the allocator assigns a fixed number of pages to the container, and the agent then updates the memory limit of the container CI. However, if the memory cannot be reclaimed, then there is no other option but the OS kills the container. So, this is how the algorithm works. Finally, let's take a look at how ESCRA can be employed in serverless environments. Serverless workloads are characterized by being short lived and highly multi tenant. In fact, 90% of functions in these environments run in under 1 minute. For serverless environments, ESCRA seamlessly integrates with OpenWhisk and uses its container pool's memory limit to set a global application memory. And then pod affinity is utilized to ensure that both infrastructure and user actions run on dedicated nodes. And although there is no native CPU limit, but ESCRA scales CPU linearly with memory. Additionally, ESCRA ensures that container creation is not delayed during scaling, that allows it to work efficiently with Kubernetes. So this is how ESCRA can be integrated into serverless environments. So how does all this align with what we have learned so far? ESCRA reflects several key distributed system concepts from class. It first of all maintains a global state using real-time telemetry and a shared memory pool. Then, for concurrency control, ESCRA dynamically manages multiple containers which compete for CPU and memory and ensures fair allocation. And though not a classic peer-to-peer system, ESCRA's P2P like coordination is evident in how it distributes decision making across containers, and it also leverages gRPC for lightweight and scalable communication between components. So this is how the ESCRA architecture is and how the algorithm works. Now let's dive deep into how ESCRA can be implemented and it's, let's say, it's performance evaluation.
Okay, let us now talk about the implementation details of ESCRA. So the controller and allocator use C++, are implemented in C++, and they use remote procedure control to talk to deployer, watcher, and agents, which are written in Go. Deployer uses Kubernetes deployment API to create containers, whereas container watcher hooks into Kubernetes WorkQueue API to detect the creation of containers. Docker is used as the underlying container runtime. Each worker runs a custom Linux kernel, which hooks into the CFS group and memory subsystems. And this custom Linux kernel also contains a custom message structure for reporting CPU, telemetry, memory memory allocation request to controller. Now let us talk about the experimentation and evaluation part. 4 benchmark applications are considered, and 4 workload types are considered. Fixed exponential burst, which is fixed mixed with a sudden burst of exponential workload, and Alibaba trace, which is a real live cloud workload. 3 valuation metrics are considered: absolute slack, throughput, and 99 percentile latency. And the baselines are Google's Autopilot's auto-scaling mechanism and static allocation, where the container limits are set to 1.5 times peak usage, and the peak usage is determined from container profiling. Now, let us look at the performance plots. Let us consider the performance statistics of ESCRA versus static allocation first. While static allocation occasionally achieves higher throughput, ESCRA generally outperforms. This is because the container profiling, using which static allocation's peak usage is determined, it has a very unpredictable nature of accuracy, because the workload in real life is really unpredictable in nature. Now, ESCRA's ability to dynamically reallocate resources amongst containers is also a major reason why it achieves its superiority in performance over static allocation workload, which cannot dynamically reallocate resources. Now let's talk about the performance statistics of ESCRA versus Autopilot. In most situations, especially in dynamic workload situations, ESCRA outperforms Autopilot because Autopilot, unlike ESCRA, relies on coarse-grained data, which makes it unable to adapt to dynamic workload situations. In certain cases, Autopilot, however, marginally surpasses ESCRA because it sacrifices slack by assigning excess resource limits to containers in order to maintain performance. Now let's look at the slack CDFs. So we find that ESCRA shows consistent improvement in percentile and 50 percentile and 99 percentile CPU slack, uh, as evidenced by the curves over here, where ESCRA curves are all on the leftmost part. Now for memory slack, we find that we get mixed results for 50 percentile case, whereas for 99 percentile case, we see consistent performance where ESCRA outperforms the other 2 baselines. Now, an average table is also given, which computes basically the average slack, latency, and throughput for and basically compute its difference between ESCRA and its baselines across all app workload combinations, and it shows that ESCRA offers significant improvement and thereby takes an optimal step towards achieving performance cost efficiency trade-off. Now, our combined insights from these performance plots and Slack CDF show that ESCRA consistently outperforms Autopilot and static allocation by a significant margin, where in rare cases where ESCRA underperforms, the drop is minimal, whereas the Slack improvement is still appreciable. Now, let us take a look at the second kind of benchmarking applications which the authors consider, which is the serverless benchmark application. And 2 applications are considered over here: image process, which is an image processing application with constant workload, and grid search, which is basically a hyperparameter tuning application for ML models, which also has a constant workload. 2 evaluation metrics are considered: aggregate limit and application latency. Now, latency CDF, which we see for image process, shows us that OpenWhisk plus ESCRA on an average performs better in terms of latency than OpenWhisk alone. And the fact that the tail latencies match show, in fact, that ESCRA effectively handles dynamic scale-up of containers, which OpenWhisk alone, which is a good thing because it is very much essential for orchestration mechanism to do that in serverless environments. Furthermore, for the grid search application, we find that ESCRA plus OpenWhisk achieves lower 99% latency than OpenWhisk alone. And the surprising thing over here is for the case for look at the green plot in the graph over here. It's basically ESCRA plus OpenWhisk, but with 20% less resources than the case where OpenWhisk is used alone. Even with lesser resources, ESCRA plus OpenWhisk achieves near similar latency. And in fact, and authors say that the latency is only higher than the OpenWhisk alone case by 1%. Now, the aggregate memory and CPU limits for image process application shows that there are significant memory and vCPU savings. And the same thing is observed for grid search as well. Therefore, ESCRA reduces resource usage significantly while keeping function latency nearly unchanged. Furthermore, as we saw that the rapid scaling process and rapid spot scaling in image process and the fact that ESCRA plus OpenWhisk can run data-heavy, long-running grid search jobs efficiently shows with fewer resources that too shows that ESCRA is a truly versatile model. Now, limitations which present potential avenues for future work are like, first of all, we noticed that no study has been performed on the sensitivity of the performance of ESCRA with different hyperparameter combinations. Secondly, in predictive, we see a very natural predictive modeling opportunity where, based on fine-grained telemetry data, only a simple extrapolation model has been used in this paper, where a sophisticated ML-based prediction model can be used, which can utilize effectively the nonlinearity in the telemetry data, to basically obtain better predictions. Now, while ESCRA's performance have been validated in simpler situations, the main thing which the authors agree as well is the fact that whether ESCRA can scale up in large-scale deployments with diverse workloads and multiple tenants. Thank you so much. This was our presentation.